Hello guys, in this session we will be discussing the ISRO previous year questions. So if you group all the ISRO previous year questions at one place, and if you see from which area the questions are being asked very frequently or in a higher number, that's from mechanical vibrations, guys. Okay. So from 2006 onwards, if you gather all the ISRO questions, so there are around 90 to 95 questions from theory of measures. And out of these 90 to 95 questions, 52 questions are from mechanical vibrations, guys. Mechanical vibrations is a very important topic for GATE. And similarly for ISRO also, it is a very important topic. So for those students who don't have time to go through the complete theory of machines subject, I suggest please go through vibrations at least, because vibrations is very important. Every year you can expect 2 to 3 questions from mechanical vibrations, guys. Okay, so let's start our discussion. We'll solve some questions. And one more important thing I want to tell you people before we start discussing this ISRO previous year questions. That is, the approach should be different for ISRO exam and for GATE exam, guys. Many of you who are appearing for ISRO exam, so they might be preparing for GATE and they might have already given GATE. So the number of questions in GATE and the time and the number of questions in ISRO and the time that you are going to get are entirely different, guys. You get more number of questions, less time in ISRO, whereas in GATE, you get less number of questions and more time. And apart from that, you will be having access to the calculator. In ISRO exam, you will not have access to the calculator. The number of questions are more. You get close to 80 questions. And the time is also less, guys, less than 3 hours, I think it's. Yeah, if I'm not wrong. Yeah. So your approach should be different for ISRO exam. So you should solve the questions at a faster rate, guys. Don't waste time on any particular question if you're not getting the answer, guys. Okay. So don't give a lot of time to one question. I suggest please have a look at the complete question paper and try to attempt all the easy questions first, and then go for the mediums, and the hard questions attempt at the last, guys. Okay, so if you answer any tough or a complex question, you are not going to get any reward, guys. Or remember that. Okay, so many students feel satisfied by attempting a complex question, and at the same time they forget that they are wasting a lot of time in attempting that particular question, guys. Your marks will matter. So which question you have answered, that doesn't matter, guys. It's a competitive exam. So don't fool yourself. So be active, be energetic. So time is very important and the speed is very important. So keeping that in mind, start your exam, guys. Okay. So let me discuss some of the questions that you get in previous ISRO. Like I said, the vibrations topic, mechanical vibrations topic is very important. 50% of the questions, previous questions, guys, if you club all the questions, more than 50%, I can say, out of 90 questions, 50 to 51, I think exactly, 51 questions are from vibrations. You can imagine that. Okay, so this is a very important topic, and this is a very easy topic, guys. So mechanical vibrations is a very easy topic for both GATE and ISRO. You can easily get marks, guys. You don't need to remember a lot of formulas in mechanical vibrations. Okay, so let's start our discussion with the first question. So this is the first question, guys. Go through this question. A machine component of 90 kgs mass. So mass of this machine component is given. It is 90 kgs, guys. It is held in this position using these springs, 3 springs shown below. The spring constants K1, K2, and K3 are 4, 4, and 8 Newton per meter respectively. Find the natural frequency of the system, guys. So when our springs are clubbed like this and you are given a mass, so the natural frequency, we have solved a lot of problems like this, previous GATE questions. We find the frequency as under root K equivalent by M. What is the equivalent stiffness of these two? These two springs are connected in series. The equivalent stiffness is K1, K2 divided by K1 plus K2, guys. And now this K1, K2 by K1 plus K2 and this K3, now they are in parallel. So the equivalent stiffness, the total equivalent stiffness will be K3 plus K1, K2 divided by K1 plus K2, guys. So this is the equivalent stiffness, okay? So the equivalent stiffness, so what is this K3? K3 is given in the question. This is 8 Newton per meter plus K1, K2. So this is 4 into 4 divided by 4 plus 4. You find the equivalent stiffness, guys. You are not allowed to use calci. So this is 10 Newton per meter. This is the equivalent stiffness. So once you get the equivalent stiffness, mass is given in the question, you can get omega n. Omega n is under root K equivalent, that is 10 by mass is 90. So this is close to 1 by 3 radian per second, guys. So 1 by 3 radian per second. So it is 0.33 radian per second, guys. This is the natural frequency of the system. So option A is the correct answer, guys. So you should be very fast in solving this kind of problems, guys. It's a very simple question. You should not waste a lot of time, okay? Yeah. Let's get on to the next question. A driver of mass 100 kg is standing on the tip of a springboard of negligible mass. The natural frequency of springboard with the diver, sorry, it's not driver, it's diver, is, so the frequency is given, guys. So for the diver, so the frequency is this many heads, okay? Natural frequency of a springboard with the diver is 1.6 heads. What is the static deflection at the tip of a springboard when the diver is standing at the tip? So this is similar to a problem that we have in gate. So that is a cantilever beam which is of massless, a point mass is there at its end. So what is the natural frequency of this system? We solve this problem using a static deflection method. So here also we use the same thing, guys. So according to static deflection method, natural frequency omega n is under root g by delta. What is this delta? So because of that mass, so this beam will undergo some deflection. What is the deflection of this mass? So you need to find that. So deflection for a cantilever beam having a mass at its tip is WL cube by 3EI, guys. WL cube by 3EI. So this we have solved in our class. So it's a previous gate question similar to this. We have a similar previous gate question, guys. So now, so omega n is, so I'm substituting for delta. So this is 3EI divided by ML cube. Okay. So we don't need to find this. I think we just need to find the value of delta. It's just asking the static deflection, guys. So we directly need to find this delta. We are not worried about all these things. We can skip that. So the frequency is given in heads. How to write frequency in heads? So those who are prepared for GATE, they might be knowing this. And for someone who is looking at these lectures for the first time, so we have this formula, guys. The time period is 2 pi by omega, okay? Time period is 2 pi by omega. And the frequency in heads is nothing but the reciprocal of time period, guys. So this is the linear frequency. Its frequency is the reciprocal of time period. So the unit is heads. What is the unit of this? The unit of this is in radian per second. If they ask in radian per second, you have to use this. If they ask in heads, you have to use this, guys. So the frequency in heads is 1 by time period is nothing but, so omega n. So this is omega n. So this is Fn, so divided by 2 pi. Omega n by 2 pi is given as. Omega n divided by 2 pi is given in the question, 1.6. What is omega n? Root g by delta. Omega n is under root g by delta. G is 9.81 divided by delta. So this is 1.6. So you simplify this and get the value of delta, guys. That is the static deflection. So the value of delta is 0.097 meters. This is the static deflection. So this is a static deflection. So I can say it is roughly 97 mm, guys. So the closest answer that we are having here is 98.1 mm. So option C is the answer, okay? Yeah. Try to answer this question. It's a very simple question. In vibration isolation, if omega by omega n is less than √2, what will happen to the transmissibility? So this question is from transmissibility. So in transmissibility, we have discussed, we have plotted a graph. So between, so the transmissibility and the frequency ratio, guys. So transmissibility and the frequency ratio, transmissibility and frequency ratio, omega by omega n ratio. So we have seen this graph. So I said this graph is very important. So we have a lot of questions in engineering services exam and GATE as well. So this is transmissibility 1, and so we have one more point over here. So this is a point of resonance for undamped vibrations. This is omega by omega and it's 1. And so if I plot a graph for different values of zeta, so the transmissibility will be varying like this, guys. And for a different value of zeta, the curve looks like this. So if you remember, so all the curves, they pass through one single point here. And this point, if you remember, so this is where the frequency ratio, omega by omega n ratio is √2, guys. So this is for different values of zeta. So maybe for this is zeta is 0, and for this curve, zeta is 1. Zeta will be increasing, guys. And for this curve, zeta is, I'm really sorry. So this is less than 1, basically. So this may be 0.1 and this may be 0.2, guys. Okay, so we have vibrations only for underdamped systems. Zeta is less than 1, 0.1 and 0.2. And it will be increasing as we move inside. The outermost curve is 0. When omega by omega n ratio is to 1, that's a case of resonance. At resonance, the transmissibility will tend to infinite. And for other cases, it's not infinite. It is large. It is large. Okay. And as the value of zeta is increasing, so it means that the value of damping is increasing, guys. So more damping, so more absorption will be happening for the vibrations. So the transmissibility will reduce, guys. So the question here is, when omega by omega n ratio that is less than √2, what will happen to transmissibility? So you can see this graph. So when omega by omega n ratio is less than √2, so you can see this portion, guys. So the left side portion, this is √2, right? This is √2. When it is less than √2, everywhere you can see the transmissibility is more than 1, right? Transmissibility, everywhere it's more than 1, guys. So when it's less than √2, transmissibility is more than 1, guys, okay? Transmissibility is more than 1. When omega by omega n ratio is less than √2, transmissibility will be greater than 1. Everywhere it is greater than 1, guys. When omega by omega n ratio is exactly equal to √2, what is transmissibility? Transmissibility is exactly 1. When omega by omega n ratio is more than √2, so you can see transmissibility everywhere, it is less than 1, guys. It is less than 1. So we solved a similar kind of problem in the class also. It's similar to previous GATE, previous engineering services question. So if you have time, I suggest please practice all the GATE questions and all the engineering services questions, guys. So apart from the ISRO questions, okay? The natural frequency of a simply supported beam of length L and mass m at the center. So the fluxurial rigidity is given. So, and he's asking us to find what is the natural frequency of a simply supported beam. So he's saying that it is a simply supported beam. And for this simply supported beam, so there is a point mass at the center. The length of this beam is L and point mass is m. The fluxurial rigidity is E. So we have already discussed a similar problem, the cantilever problem. So we solve these kind of problems using static deflection method, guys. So when the beam deflects, what will be the deflection of the mass? You first find out that. So here it is, so WL cube by 48 EI, guys. For a simply supported beam with point mass at the center, so the deflection of the mass is WL cube by 48 EI, guys. 48 EI. So according to static deflection method, so the natural frequency omega n is under root G by delta. You know the value of delta, substitute it here. So this is 48 EI divided by, so ML cube, guys. So the G and G gets cancelled. You'll be just left with, so 48 EI by ML cube. This is omega n. What is the unit of this? The unit of this is radian per second. So if you look at all these cases, so we have this 1 by 2 pi. So, but we don't have any 1 by 2 pi over here. So it means that the frequency is given in hertz, guys. So you need to convert this into hertz. I already told you. So what is the time period? So time period is 2 pi by omega n. The frequency in hertz is nothing but the reciprocal of time period. So it is omega n divided by 2 pi, or you can write it as 1 by 2 pi into omega n. So it is 48 EI divided by ML cube. This many heads. Or we can also say cycles per second, guys. So 1 by 2 pi 48 EI by ML cube. Option A is the answer. So these are very simple questions. So if you have practiced previous gate questions, or at least if you have gone through the classes, guys, okay? And try to answer this question. This is also a similar question, but this is, we don't have this particular topic for the GATE syllabus. I mean, not many questions in GATE, but in engineering services, you find questions from this particular topic, guys. So this is vibrations due to support motion, okay? A machine component of natural frequency, so 20 radian per second, is subjected to, so a base motion from the machine, which is harmonic in nature, with an amplitude 3 meter per second square at 10 radian per second, okay? What is the peak amplitude of relative displacement of the components if damping is negligible, okay? He's asking us to find out, so the peak relative amplitude. So we have this formula. So amplitude is, so F naught by K divided by under root 1 minus omega by omega n whole square plus 2 zeta into omega by omega n whole square. Okay, so in this question, if you see, so he said somewhere, so if there is no damping, okay, so what is the peak amplitude of relative displacement of the components if the damping is negligible? So damping is not given in the question. So he said it's negligible. So I ignore the value of zeta, guys. So I am assuming zeta is 0. I'm assuming there is no damping in the system. So the amplitude, so this is F naught by K divided by 1 minus omega by omega n whole square. So if you go through the question, guys, so what is omega? So machine components of natural frequency, omega n is given. So the natural frequency of the machine components is given as 20 radian per second. So he's subjected to a base motion from the machine, which is harmonic in nature. He's saying that, so the machine components are subjected to a base motion. So basically it is nothing but the excitation motion, guys. So the amplitude of excitation motion is given as, so 3 meter per second square. So we have this excitation force. So this F naught is me omega square. So the product E omega square is nothing but the amplitude of the excitation motion, guys. So this F naught is ma max. So the amplitude. So this I'm writing like this. This A max, I'm writing this, I'm making this as subject. So this is F naught by M. So this is given in the question. So this is given as 3 meter per second square. So F naught by M is given as 3 meter per second square. So at an excitation frequency, the excitation frequency is omega. So that is given as 10 radian per second. Omega n is given in the question. Omega is given in the question. And we know the amplitude of the base motion, that is 3 meters per second square. Okay. So we need to find this amplitude. So we don't know this F naught, guys. So, but I know this F naught by M. So I multiply and divide with M, guys. This K by M divided by 1 minus omega by omega n whole square. Omega is 10. Omega n is 20 whole square. Okay. So F naught by M. So F naught by M is 3. So divided by K by M. What is K by M? K by M is nothing but omega n square, right? Omega n is root K by M. So omega n square will be K by M, guys. So omega n square. Omega n square. K by M is omega n square. So this is 1 minus 1 by 4, guys. So this is 3 divided by 400 divided by, so this is 3 by 4. This is 3 by 4. If you simplify this, you get 1 by 100, or I can say it's 0.01 meters, guys. 0.01 meters is nothing but, so 10 mm. So the relative amplitude here is 10 mm, guys. Relative amplitude here is 10 mm. So this is basically from forcing due to support motion, okay? Try to answer this question, guys. Try to answer this question. This is, again, a very simple question. So if the natural frequency of spring mass system on Earth is F, so the natural frequency of a spring mass system on Earth is F, its natural frequency on Moon, so where acceleration due to gravity is 1/6 of that of Earth. He's saying that, so the acceleration due to gravity on Moon is 1/6 of Earth. What will happen to the natural frequency of the spring mass system, guys? So there won't be any change, guys. The natural frequency is going to remain same. So if you look at the frequency of a spring mass system, so omega n, so it is root K by M, guys. For a spring mass system, the natural frequency is root K by M. So it's not depending on G, right? It's not depending, it's independent of G. So whether it's on Earth or whether it's on Moon, the natural frequency will remain same for a spring mass system, okay? So remember this, guys. If the vibrations are happening, so because of the internal stiffness, so in such case, so the natural frequency will not become a function of any other parameter, guys. The natural frequency of the system depends on its own structural properties, okay? Its own structural properties. If the vibrations are happening because of some external fields, then it depends on that particular field. If I take a simple pendulum, so if you see the natural frequency of simple pendulum, guys, so the natural frequency of simple pendulum, or the vibrations in simple pendulum. So how the vibrations happen in simple pendulum? Because of gravity, right? So if I displace the pendulum will come back to its original position, or it will be oscillating because of the gravitational force. If there is no gravity, so the pendulum that you displace, will it come back to the mean position? So it will not come back, guys. So in a simple pendulum, the vibrations or the oscillations are happening because of gravity. So the natural frequency is a function of gravitational constant. So if you go to Moon, gravitational constant changes, natural frequency changes for a pendulum. But for a spring mass system, the vibrations are because of stiffness of the spring. The stiffness of the spring will not change when you go to the Moon. So the natural frequency doesn't change, guys. So in this case, the answer is F. If it is a simple pendulum, then it will change, guys. Okay. So for a spring mass system, it doesn't change. So try to answer this question. A perfectly balanced rotor shaft is supported between short bearings at both ends, shows a deflection of 2 mm at the middle. So then the critical speed of the shaft in RPM will be nearly. He's asking us to find out the critical speed, guys. So whenever you come across this word, the critical speed or the whirling speed or the dangerous speed or the whipping speed, is nothing but the speed at which the system catches resonance, guys. What is the speed at which the system catches resonance? The system catches resonance when the speed of the shaft is exactly equals to the natural frequency. When the speed is equals to natural frequency, at that point of time, so the amplitude will be increasing with time, so there will be violent vibrations. And at this particular speed, since the amplitude is increasing and the vibrations are violent, it is called as the critical speed or the dangerous speed. Okay, so it will fail if you stay there for a longer time, guys. Okay, so we need to basically find the speed at which this happens. The speed at which this happens is nothing but the natural frequency of that particular shaft rotor system. So he's saying that, so there is a shaft and there is a rotor supported on the shaft, and these are short bearings. So whenever they use the word short bearings, you have to treat this as a simply supported beam. So whenever they say it is long bearings, you have to treat these supports as fixed supports, guys. Okay, it's not a cantilever beam. Sorry, it's not a simply supported beam. In such case, it will be a fixed beam. So the beam is fixed at both the ends when they are long supports, long bearings. When it's a short bearing like this, so you can treat this as a simply supported beam. So in this question, he directly gave the deflection. So the deflection is given as 2 mm. So that is 2 into 10 power minus 3 meters, guys. You can find the natural frequency. Omega n is under root g by delta. So g is 9.81. So delta is 2 into 10 power minus 3. You simplify this and get the value of omega n. Omega n is under root g by delta. So this is close to 70 radian per second, guys. He's asking us to get the answer in RPM. So the speed, when the speed becomes equals to the natural frequency, we will have resonance, guys. So what is this 70 radian per second in RPM? So I'm writing like this. 70 is 2 pi into n by 60. You simplify this and get the value of n, guys. 70 into 60 by 2 pi. So it is close to 668.45 RPM, guys. So it is 670 RPM. 670 RPM. It's also a very simple question. So I think, so we are using the same concept, static deflection method. So far, we have used 3 times, guys. Okay. So try to answer this question, guys. For the spring system given in the figure, the equivalent stiffness is. What is the equivalent stiffness, guys? For the spring system given in the figure, so what is the equivalent stiffness? So the equivalent stiffness, these 2 springs are clubbed in parallel. So the stiffness is 2K. And this one and this one, so they are in series, guys. So in between, you just have a rigid bar. It's not a mass. So these 2 are in series. So what is the equivalent stiffness for series combination? K1, K2 divided by K1 plus K2. So K1 is, what's the value of K1? It is 2K, and the value of this also 2K. So this is 2K plus 2K, guys. So this is 4K square divided by 4K. So the stiffness is K, guys. In this case, the equivalent stiffness is K. Yeah. So try to answer this question, guys. So remember this, guys. Whenever 2 springs are clubbed in parallel, okay? So for parallel combination, so whenever you see the springs like this is parallel combination, okay? This is parallel combination. So this is K1 and K2. The equivalent stiffness is K1 plus K2, guys. This is also parallel combination, okay? So whenever you see the springs connected like this is also parallel combination, guys. This is also parallel combination. K1 plus K2. Remember one thing. So in parallel combination, the load, this mg force is shared by both the springs, right? In parallel combination, the load will be shared, guys. And what about the deflection? The 2 springs will undergo same deflection. Here, this mg force is again acting on these 2 springs. Load is shared. Again, the deflection is same, guys. If the mass comes down by 1 meter, so then both the springs have 1 meter deflection. Okay. If the 2 springs are sharing the load and the deflection is same, that's a parallel combination. And this is series combination, guys. This is one spring K1. This is another spring K2. So this is series combination. Okay. In series combination, if I ask you what is the deflection of the mass, deflection of the mass is nothing but what is the deflection in first spring plus what is the deflection in second spring. By how much amount spring 1 is getting deflected, by how much amount spring 2 is getting deflected. You add both of them. That is the deflection of the mass. So deflection is sum of individual deflections. Okay. And so the equivalent stiffness here is K1, K2 divided by K1 plus K2. So keep these two formulas in mind, guys. So these two are parallel combinations and this is series combination. Now you know, I think, how to find the equivalent stiffness for parallel and series combinations. So that's what I did. These two are parallel combinations and this one, this 2K and this 2K are now again in series combination. So that way I found out the equivalent stiffness, guys. We will be using this very frequently, okay? So try to answer this question. So if the length of cantilever beam is reduced to 1/4, the natural frequency of the mass M at the end of this cantilever beam of negligible mass will be increased by a factor of what? So he's saying that, so there is a cantilever beam. This cantilever beam is massless and there is a point mass at the end of this cantilever beam and that's vibrating. What will happen to the frequency of that when we reduce the length to 1/4, guys? So if L is the length of this, so to find natural frequency of this, we need to find what is the deflection of this mass. So deflection of this mass for a cantilever beam, if there is a point mass at its end, the deflection is mg L cube by 3EI, guys. This is the deflection. First, find the natural frequency. What is the natural frequency, guys? We find natural frequency using static deflection method. Okay, so what is the formula as per static deflection method? Omega n is root g by delta. You know the value of delta. So substitute the value of delta, guys. If you substitute the value of delta, it is 3EI divided by ml cube. So if you look at this problem, so the natural frequency is inversely proportional to L power 3 by 2, right? L power 3 by 2, guys. I'm writing like this, omega 1 by omega 2. So this is L2 divided by L1 power 3 by 2. What is L2, guys? It is L by 4. And what is L1? L1 is L, so power 3 by 2. So this is omega 1 by omega 2. So this is 1 by, so this 4 I am writing it as 2 square power 3 by 2. So this square and this root will get cancelled. So you will be left with, so omega 1 by omega 2. Omega 1 by omega 2 is, so 1 by 2 power 3 is 8, guys. So what will be the new natural frequency? So omega 2, you can see this is 8 times omega 1, guys. So it will be increased by what factor? The factor is 8, guys. The new natural frequency is 8 times omega 1. That's a very simple question. So wherever you see these kind of questions, guys, a simply supported beam or a cantilever beam, okay, so whenever there is a mass and you want to find the natural frequency, we use static deflection method. So what is static deflection method? So if you know the static deflection, we can find the natural frequency using this mass. So this delta is the deflection of the mass, static deflection of the mass. So if you keep this mass here on the beam, by how much amount it will deflect? So you need to find that. How do you find that? So we find this using strength of material concepts. In strength of materials, you might have studied about this slopes and deflections topic. So we get this from there, guys. So try to answer this question, guys. This is a very interesting question again. Okay. So which of the following is true for vibrations of a mechanical system? Okay. So for mechanical vibrations, which of the following statement is true? The damping ratio zeta is the ratio of critical damping to actual damping. This is wrong, guys. So what is this zeta is actual to critical damping. Okay, so it's not critical to actual. It is the ratio of actual damping coefficient to critical damping coefficient. Okay. So the second one is the damping can be obtained from the response of the system under forced vibrations using logarithmic decrement method? No, guys. So it is little difficult to understand in forced vibrations. Okay, you don't get a clear idea. So in forced vibrations, so if it's not forced vibrations, if it is forced vibrations, what will happen? If it's forced vibrations, the vibrations will never die, guys. Vibrations will never die. The system will vibrate with the same amplitude throughout. As long as there is an external force, the system continue to vibrate with the same amplitude. So you don't get a clear idea about the damping. You don't get you cannot find what is damping. You don't get any clear picture about damping. If it is not forced vibrations, then so you can find the damping, guys. How you can find? So if it is not forced vibrations, what will happen to the amplitude? Amplitude will be decreasing, guys. At what rate the amplitude is decreasing? If you can find that, so that gives you the damping, guys. Okay. So the damping indicates if the damping is more, the vibration amplitude will reduce faster. Damping means friction. If the friction is more, energy will be lost at a higher rate. The amplitude will reduce at a higher rate and the vibrations will stop quickly, guys. But in forced vibrations, the vibrations will never stop as long as the force is present. So you don't get a clear picture for that. And this option for damped mechanical systems, the amplitude of vibrations tends to infinite when the excitation frequency reaches the system's natural frequency, guys. So he's saying that the amplitude will tend to infinite at omega by omega n ratio 1, guys. So you might have seen this graph of magnification factor. So this also works good for amplitude, guys. Amplitude versus frequency ratio or magnification factor versus frequency ratio, both the graphs look the same. So if you look at this case, so the amplitude or the magnification factor was tending to infinite. So the amplitude or the magnification factor will tend to infinite. So only for undamped systems, guys. So when omega by omega n is equals to 1, or I can say, what is this? Omega by omega n is equal to 1. So it means that when omega is close to omega n, so when the excitation frequency is close to natural frequency, the magnification factor or the amplitude will tend to infinite only for undamped systems, guys, not for damped systems. Many people have a confusion in this. Okay, so it's only for undamped systems. For damped vibrations, so there is some maximum. So, but it's not tending to infinite, guys. Okay, it's not tending to infinite. Okay, it's not tending to infinite. It's not tending to infinite. It is maximum when the frequency is closer to omega n. So, but it's not infinite. It doesn't tend to infinite, guys. So this is also not correct, truly speaking. But many people assume this as correct, but that's wrong, guys. So amplitude ratio and transmissibility of vibration isolator. So it's vibration isolation topic, the transmissibility. So the amplitude ratio and the transmissibility, guys. So these two is unity. So when the frequency of excitation force is √2 times the natural frequency. He's saying that, so when omega by omega n is √2, so what about this, the amplitude ratios, means the magnification factor, and what about the transmissibility? So transmissibility graph we have seen in the previous problems. The transmissibility curve, so when the frequency ratio is exactly √2, guys, what is transmissibility? It is 1. But it doesn't hold good for all the cases. So the amplitude, transmissibility is 1 always when the frequency ratio is √2, guys. That holds good. The amplitude ratio doesn't hold good for all the cases, but there are certain cases where, so the amplitude ratio is 1 when the frequency ratio is √2, guys. So in this region. So this option is more appropriate. So in the given options, guys, the given option, this is more appropriate. This is much correct one. Okay. So he would have made option D more accurate. So, but the amplitude ratio, so it is valid for some cases, but not for all the cases. But the transmissibility ratio holds good for all values of zeta, guys. So for some values of zeta, so this may be zeta 0.1, 0.2, and so on. So this is 0.2, zeta 0.2. So for some values of zeta, so the amplitude ratio will be equal to 1. So when the frequency ratio is √2, but not for all the cases, guys. Okay. So try to answer this question, guys. This is again a very simple question. We solved similar questions so far like this. Yeah. A mass of 2 kg is attached to two identical springs, each of stiffness 40 kilonewton per meter, guys. The stiffness is given 40 kilonewton per meter. It is asking us to find out the natural frequency, guys. It is frictionless. We need to find the natural frequency in hertz. So we solved a similar kind of problem. So it's a combination of springs, guys. The natural frequency, how do you find? Under root K equivalent by M. So whenever you see multiple springs clubbed in series or parallel, natural frequency is root K equivalent by M, guys. What is K equivalent? How are the two springs connected? They are in parallel. You just add both of them, so by M. So omega n is under root, so 2K by M. So what's the value of K, guys? So K is 40. One important thing that you need to keep in mind, guys. So whenever you are writing under root of K, so root kilo is not defined, guys. Many students keep this K as kilonewton per meter. Never do that mistake. So you always have to write that as Newton per meter. So never write kilo in under root. So you have to write that as Newton per meter. So divided by mass, mass is 2 kg, guys. Omega n is, so 4 into 10 power 4, or I can say 2 into, so 10 square. So this is omega n, guys. So we need to find that in hertz. So this is omega n by 2 pi. Divide that by 2 pi, guys. So this is 200 divided by 2 pi. Simplify this, you get something close to 31.8 hertz. So the closest answer is 32, guys. These are very simple questions. Yeah. Let's continue the discussion. Yeah. So look at this problem. It's again a very simple problem. So most of the questions that are from vibrations, you don't need to remember any formulas, guys. Okay. Very simple formulas and very easy questions. Okay. So the reading of a spring balance is from 0 to 200 newtons, guys. So the spring balance, the reading is from 0 to 200 newtons and is 10 centimeters long. The spring is 10 centimeters long. A body suspended from the spring balance is observed to oscillate vertically at 2 hertz. So the mass of the body is, so he's asking us to find what is the mass of the body. And he gave the frequency, guys, okay? He gave the frequency and he gave the spring balance, the maximum load it can carry is 200 newtons. And he gave the length also, okay? He gave the length of that particular spring as well. So, I mean, for this 10 centimeters length, so this 200 newtons will be taken, guys, okay? So as the load increases from 0 to 200, so that will be, this 10 centimeters length will be used for showing that, so 0 newtons to 200 newtons. So what does that mean? So it means that, so for this total load, 200 newtons load, so the deflection will be 10 centimeters, guys. So I can write like this, the spring force F is nothing but K times delta, right? So the total load, the maximum load that it can support is 200 newtons. And the maximum deflection the spring can have is 10 centimeters. So this is K into, so the deflection is 0.1 meters, guys. So K, if you simplify this, you get some 2000 Newton per meter. This is the stiffness of the spring. So we need to find the mass, we know the frequency in hertz. Omega n, I'm writing like this. Omega n is root K by M. So we already seen the frequency in hertz is nothing but omega n divided by 2 pi. So frequency in hertz is given in the question. It's 2 hertz. That's 1 by 2 pi into omega n is K by M. K is also given to us like 2000 and M. So we need to find the value of mass, guys. Simplify this, you get the value of mass, okay? So you should be very good in calculations, guys. You practice that. I'm very bad in calculations. I mostly use calculator, but that doesn't work for your exam. So you should practice a lot of questions, okay? So the mass is around 12.66 kgs. 12.66 kgs, guys. Okay, so while practicing for ISRO, guys, try to solve the problems without using calculator, okay? So practice previous ISRO questions without calculator. Practice engineering services questions without calculator. That should be enough. You'll get the flow. of not using the calculator. Okay, so gate questions, it is a little tough to solve without using calculator. Okay, yeah, so don't try to attempt gate questions with without calculator. It's waste of time. Okay, you can practice on what I say, engineering services questions or civil services questions, civil services mechanical paper. That can be done without calculator. Okay. So as shown in the figure, a mass of 100 kg is held between two springs. The natural frequency of vibration of the system in cycles per second is again nothing but hertz, guys. He's asking us to find out the frequency in hertz. I already told you this. So two springs and a mass. So we can find the equivalent stiffness and we can find the natural frequency. Omega n is under root k equivalent by m. So whenever you come across the springs combination and a mass, so natural frequency is root k equivalent by m, guys. So how are the two springs connected? They are connected in parallel. So 20 plus 20. So that's nothing but 2 times 20. So it is given in kilonewtons. We need to write in newtons. So I'm writing it as 10 power 3, multiplying with 10 power 3, guys. So mass is given as 100 kg. So this is omega n, guys. So simplify this, you get omega n. So this is 100 and this is 10 power 3. So you'll be having 4. So 4, you'll be just left with 20, guys. It's root 400, right? Yeah, so 400 is 20. So this many radian per second, but we want the frequency in hertz. So frequency in hertz is omega by 2 pi. So this is close to 10 by pi radian per second. Sorry, hertz. So option C is the answer, guys. Try to answer this question. The fundamental natural frequency of the cantilever beam with point load P acting at the free end is. So we are solving similar kind of questions if you notice, guys. So the same question. So we already solved this. It is a cantilever beam. So with a point load P at its tip, what is the natural frequency? You find the deflection here. So what is the deflection, guys? So deflection is WL cube by 3EI. So once you know the deflection, you can find omega n is under root G by delta. Substitute for delta, guys. Substitute for delta. So this is 3EI divided by ML cube, guys. So it's not M, it's PL cube. PL cube, so we are not cancelling the G, so G will also be there. So 3EI into G divided by PL cube, guys. So option A is the answer, guys. Yeah. So this is again a very simple question, very basic mechanics question. So try to answer this, guys. So the potential difference, the difference in potential energy between two arbitrary position, the downward displacements x1 and x2, and he's saying that x2 is more than x1. So x is nothing but the deflection, guys. He gave two deflections, x2 and x1. So what is the potential difference? The difference in potential energy basically between these two positions. One important thing that you need to keep in mind here. So when you're dealing with the spring mass system, guys, when you're dealing with spring mass system, so this is the free end of the spring, guys. This is the free end of the spring, okay? This is the free end of the spring. The spring is massless. So no mass is connected to it. So when you connect a mass to it, guys, what will happen? When you attach a mass to it, the spring will undergo some deflection and it will settle in an equilibrium position, guys. So this deflection is called as static deflection. Now what happens? It settles in an equilibrium position. You attach the mass, the spring will undergo some deflection and it settles in an equilibrium position, guys. Now this mg force and this k delta naught force, so these two forces will be equal in magnitude and opposite in direction, guys. Opposite in direction. So this story is not given in the question, right? This story is not given in the question. So they directly gave a spring mass system. In vibrations, whenever you see a spring mass system, you have to assume that the system is in static equilibrium position. It means that already, so the spring has undergone some deflection delta. Okay, so this K delta naught force and this mg force, they are equal in magnitude and opposite in direction, guys. So to keep the calculations simple in vibrations, whenever you are dealing with spring mass system, don't consider that mg effect, guys. Don't consider this mg effect. Don't consider this K delta effect. K delta naught effect. So don't consider both the effects. If you consider mg effect, you have to consider the K delta naught effect. So I don't consider both of them. So when I'm not considering the effect of mg, there won't be any effect of the gravitational potential energy, guys. There is no gravitational potential energy. The spring which is vibrating here, the spring mass system which is vibrating, it is independent of G. It is independent of G. It's independent of gravitational potential energy, guys. We just have to consider the potential energies of the spring only. We should not consider the potential energy of the gravitational potential. If you want to consider the potential energy, then consider it. But along with that, we have to consider this delta naught effect also. So we generally ignore that. So there won't be any gravitational effects on the spring mass system. That's taken care, that's already cancelled. Okay, that mg effect and k delta effect, they got neutralized. Now, so when I stretch this spring by x2 amount, what is the potential energy of the spring? The potential energy will be half kx square, kx2 square. So if I stretch the spring by x1, so then the potential energy will be half kx1 square. He's asking us to find the difference between them. So this is the difference between them, guys. So when the spring is stretched more, the potential energy is more. When the spring is stretched less, the potential energy will be less, guys. Okay. So half k x2 square minus x1 square, guys. That's the difference in potential energies. So, sir, when there is a difference in x2 to x1, so when I bring the mass to x1 or when I bring the mass to x2, the potential energy is changing, right? It's decreasing. Yes, it's decreasing. If you consider the effect of decreased gravitational potential energy, you have to consider this k delta effect also. These two will cancel each other, guys. Okay. So if you want to do all that, you can do that. Okay. You can write, so what is the potential energy of the mass? So you can assume some initial potential energy as P1. So when the deflection is x1, you can find what is the potential energy. When the deflection is x2, you can find what is the potential energy. And you rearrange the terms using this k delta and mg. So some terms will get cancelled out. You will be left with this. The simple idea here is the spring mass system, there is no gravitational effect, guys. It's no gravitational effect. The gravitational effect is already cancelled with the initial deflection of the spring. So to keep the problem simple, in all spring mass systems, there is no gravitational effect. There is no gravitational potential energy. So there is no the delta naught effect. If you consider the delta naught effect, you have to consider the gravitational potential energy effect. G will be coming into picture, guys. So I don't consider both of them. So most of the problems we have solved in the same way. So this is a very good question, guys. I can say this is the only question that's slightly difficult. Not difficult, it's slightly lengthy question in entire ISRO previous papers, okay? So try to answer this question, guys. So determine the equivalent mass and equivalent stiffness, so for the system in the below figure, okay? So when x, so the capital X, so the downward displacement of the block M, so X is the displacement of the block M, measured from the system's equilibrium position, is used as the generalized coordinate. So take I as moment of inertia of the wheel. So considering the moment of inertia of the wheel, so we need to find what is the equivalent stiffness of this particular system, what is the equivalent mass of this particular system. So whenever you come across these kind of problems, guys, first you develop a mathematical model which is governing this particular system, guys. So here, if you look at this particular problem, so the disk is hinged here, guys. So the disk is hinged here. So assume this. When I give a small angular displacement theta to this particular disk, I give a small angular displacement theta to the disk and I leave it. What will happen, guys? So the disk will be rotating back and forth, back and forth. When the disk is rotating back and forth, what will happen to the point mass? This point mass will be moving up and down. This spring will be getting compressed, elongated, compressed, elongated. This spring will also get compressed, elongated. So the system will be vibrating, guys. When the system is vibrating, we need to develop the mathematical model, guys. Okay, I'm writing the mathematical model. I'm using the torque method, guys. I'm giving a small angular displacement. When I leave it, so the system is vibrating about this point O, guys. So find the net moment about this point O, and you add the inertia couple. So that way, so the net couple will be 0, and we can write the equilibrium equation using the torque method or the equilibrium method for couples. It's okay, D'Alembert's principle for couples. Okay, so when I give a small angular displacement theta, so by how much amount the mass is going to come down, guys? So the mass is going to come down by x amount. What is this x? So this x in terms of theta, so when I rotate this disk by theta, So this disk or this mass will come down by an amount of r theta, guys. So the mass will come down by r theta. So the spring will be compressed by r theta. So when the spring is compressed by r theta, so there will be a spring force, right? There will be a spring force in this direction. That is kr theta is the spring force, guys. So x is the deflection of the spring, right? What is x? R theta is the deflection of the spring. If the spring is compressed by r theta, so then there will be a spring force in the opposite direction. So the spring force is kr theta, guys, okay? The spring force here is, so the spring force will be in the opposite direction. The spring force is kr theta. That's the spring force. And what about this mass, guys? This mass is moving in downward direction, right? When I rotate the disk counterclockwise, so the mass is moving downwards. So what will be the direction of inertia of this particular mass? So the inertia will be in upward direction. What is the inertia, guys? The displacement of the mass is x. So the inertia force will be x double dot, guys. What is x double dot? So x is r theta. X dot will be r theta dot. X double dot will be r theta double dot, guys. R theta double dot. So this is mx double dot mr theta double dot. So there is an inertia force mr theta double dot upwards because of this mass, and there is a spring force kr theta upwards along this line. And this spring, what will happen to this spring? The spring is stretched, right? Stretched. So there will be a spring force in this direction. By how much amount the spring is stretched? By x amount. What is this x? X is nothing but r theta, guys. Now we have found what are the external forces acting on the system. Now you find couples because of these external forces, guys. What is the couple produced because of all these forces about this point O? Okay, so I'm writing this. So because of this spring force, the couple produced is, so 2kr theta is a spring force. The perpendicular distance between these 2 points, the line of action of force and this point O is r. This is one couple. So what is the direction of this couple, guys? So what is the direction of this couple? So show all the direction of all these couples, guys. So what is the direction of that couple? So the direction of that couple is, so this is the direction of the couple. This is the direction of the couple. So this is the force. So 2kr theta is a spring force. The perpendicular distance is r. So this is the couple produced. So what is the couple produced because of this spring force about point O? It is in the same direction. It's again in the same direction, guys. It's again in the clockwise direction. The spring force now is kr theta is the spring force. The perpendicular distance is this, so into r. Kr theta into r, this is one more couple. So because of this inertia force, what is the couple produced about point O? Again, it's also in the clockwise direction. So the inertia force is mr theta double dot. So the perpendicular distance between inertia force and point O is again r. So all these are external couples. Now you add inertia couple because of this disk. In which direction we are rotating the disk? We are rotating the disk in counterclockwise direction. So I add the inertia couple in the opposite direction, guys. So I am adding inertia couple in the opposite direction. So I write like this: inertia couple for the disk. So I about point O theta double dot plus the external couples. All the couples are in the same direction. So I directly add them. So the external couples, so 2kr square theta plus this is kr theta into r. This is kr square theta plus this is m r theta double dot into r. So this is mr square theta double dot. This is 0, guys. So sum of inertia couples plus external couples is 0, guys. Okay. So this is I about point O. I mean moment of inertia of the disk basically about point O plus 2. I'm really sorry. Let me group the terms together. So this is theta double dot, right? So I theta double dot, and here I have one more theta double dot. So I naught plus mr square into theta double dot. This theta terms I'm clubbing together. So this is 2kr square and this is kr square. So this is nothing but 3kr square times theta is 0, guys. Theta is 0. So here, if you see these equations, this is mr square plus I. Yeah, so it's mr square plus I. So this is the equivalent mass into theta double dot. This is the equivalent stiffness into theta. This is 0. So natural vibrations, guys. Okay, natural vibrations. Mx double dot plus kx is 0, right? So this is the mass and this is the stiffness for a spring mass system. In a similar way, so for angular coordinates, we write like this: I theta double dot plus k theta times theta is 0. So this is the equivalent inertia of the system. This is the equivalent stiffness, guys. So here, this is the equivalent mass, and this is the equivalent, what we say, the stiffness, guys. So the equivalent mass is I plus mr square is there. So, but the equivalent stiffness, it is not 3k, it's 3k r square, guys. So, but there is no r in all the stiffnesses. R is eliminated, right? So let's try to simplify this equation further, guys. Let's try to simplify this equation further. So the coefficient of theta double dot is equivalent mass, and the coefficient of theta is equivalent stiffness, guys. I am further simplifying this statement. I am trying to eliminate this r. So I naught divided by r square plus m. I naught divided by r square plus m, theta double dot plus so 3k. I'm just dividing with r square on both sides, guys. Okay, just dividing with r square on both sides, you get this equation. So this is equal to 0, guys. It's very light pen. Yeah, this is 0. Now, what is the equivalent mass? So compare this equation. So the equivalent mass into theta double dot, equivalent stiffness into theta, this is 0, guys. So what is the equivalent mass? The equivalent mass is, this is m plus inertia divided by r square, and the equivalent stiffness is 3k, guys. The equivalent stiffness is 3k. There are 3 options, and equivalent mass is m plus, so option A is the answer, guys. So you develop a mathematical model, and so convert that mathematical model into any one of these forms. So the equivalent mass is this, and the equivalent stiffness is the coefficient of theta. The coefficient of theta double dot is the equivalent mass, and the coefficient of theta is nothing but the equivalent stiffness, guys. So for a given system, you need to develop the mathematical model. And how you develop the mathematical model? So there are different methods. You can use energy method, you can use equilibrium method for couples, or you can use any other method of your choice. Okay, so we discuss different methods and vibrations. Yeah. Let's move to the next problem. So for what values of m will resonance occur? So for the spring mass system, so given below. So with the given spring constants, so it's very obvious. You all know this. So you might be learning this from your childhood. So resonance will happen when the frequency of force will match with the natural frequency of the system, guys. Okay. So basically, you know what is the resonance frequency now? It's nothing but the natural frequency, guys. Okay. So find the natural frequency. And what is the excitation frequency? Excitation frequency is given in the question. So what is this? This is the unbalanced force, F naught sine omega into T. So the unbalanced force is 200 newtons. The frequency with which we are applying is 50, guys. Omega is 50, that's given in the question. So we need to find out what is omega n, guys. So omega n, so for this system, spring mass system, 2 springs, I write it as K equivalent by m, guys. So this is 50 is equivalent to K equivalent. So these 2 springs are in parallel. So the equivalent stiffness is K1 plus K2, guys. The equivalent stiffness is K1 plus K2. So this is 1 into 10, 2 into 10 power 5 plus 1 into 10 power 5. So this is 3 into 10 power 5. K equivalent divided by the mass. You simplify this and get the value of mass, guys. 50 squared by 3 into 10 power 5. So this is close to 120 kgs, guys. So if the mass is 120 kg, so then there will be resonance corresponding to this excitation frequency. The excitation frequency is 50. So try to answer this question. This is also a very good question, guys. It's very similar to the GATE and engineering services question. This is repeated multiple times, guys, okay? An automotive engine having a mass of 135 kg is supported on 4 springs with linear characteristics. Each of front 2 springs have a stiffness of 3 meganewton per meter, and each of rear two springs is having 4.5 meganewton per meter. It's an automobile, guys. So there are two springs at the front. So there are two springs at the rear. You know what is the stiffness of each spring, right? You know what is the stiffness of each spring. So how are the springs connected? They're connected in parallel, guys. So what is the equivalent stiffness? This is K1, this is K1, this is K2, this is K. You add all of them, guys. So the equivalent stiffness, so it is 2 times K1 plus K2, guys. The equivalent stiffness is 2 times K1 plus K2. So that is 2 times what is K1. So this is 3. What is K2? So this is 4.5. So I multiply with 10 power 6, guys, because that's given in meganewton per meter. So I just write this Newton per meter. So this is the equivalent stiffness, guys. So we need to find the resonance, the engine speed at which resonance is likely to occur. You know what is the resonance speed? So resonance speed is nothing but the natural frequency, guys. Find the natural frequency. Natural frequency is under root K equivalent by M. What is the equivalent stiffness? So this is 2. So this is 3 plus 4.5, that's 7.5 into 10 power 6 divided by, what's the mass, guys? Mass is 135 kgs. You get the speed in a radian per second, guys. So under root 2 into, so 3 plus 4.5 into 10 power 6 divided by 135. So this is 333.33 radian per second. So convert this into RPM, guys. So this is 2 pi into n by 60. You simplify this, you get the value of n. So into 60. So sorry, I got a very big answer, but that's here, it's in 10 power 4. So you get close to some 3183.06, guys. So you can check with any of these decimals. I can say it is 10 power 3, or let me check this, 10 power 4 by pi. Yeah. So option C is the answer, guys. So this is of the order like 10 power, its denominator is there. So I just verified this. So this is the correct answer. Yeah. So this is nothing but 10 power 4 by pi. If you want to verify that, you can verify. Okay. Yeah. So try to answer this question, guys. This is again very basic mechanics problem, nothing to do with vibrations, basically. Yeah. Since we deal with spring stiffness, and a lot of other things, I am keeping this question over here, guys. A weighing machine consists of a pan, so 2 kgs, okay? It consists of a 2 kg pan resting on a spring having a linear characteristic. So in this condition of resting on the spring, so the length of the spring is given as 200 mm, guys. So when a 20 kg mass is placed on the pan, so the length of the spring becomes 100 mm. So the undeformed length in mm and the spring stiffness are. He's asking us to find what is the undeformed length, and at the same time, what is the stiffness, guys. So we don't know what is the original length. Original length is L. So when you keep a 2 kg mass, what will happen? So there will be some deflection, right? So spring stiffness into, so the deflection of the spring. So initial length is L minus, so it will undergo some deflection. You will have a new length, guys. So what is the new length? So the new length was 200 mm. So this is 0.2. This is the deflection, right? Original length minus the length when 2 kgs was placed, it is 200 mm. So when I subtract L minus 0.2, so that will be the deflection, guys. So that should be equal to, so the 2 kg was supported then, so it's 2 into G. So it is something like this. So this is a spring. You don't know what is the original length. So, but when you kept, so this 2 kg, so you know what is the length. So the length is 200 mm, guys, 200 mm. So I write like this K into delta. So, I mean, K delta is a force acting in upward direction. And so this 2 into G, the gravitational force, is acting in downward directions. That is equal to 2G. So this K, what is this delta? Initial length of the spring minus final length of the spring is what is the deflection of the spring. So that is 2G. That's what I wrote here, guys. In a similar way, so K, stiffness of the spring, into delta, you don't know what is the delta. You know what is the initial length. You know what is the final length. So when how much mass is placed? When 20 kg is placed on the pan. So the pan itself is 2 kgs, guys. So when you place 20 kg again, so the total mass will be 22 kgs into g. So I got these two equations, guys. So K delta 1 is 2g, K delta 2 is 22g. What is delta 1? L minus 0.2. What is delta 2? L minus 0.1, guys. So this I am calling as equation 1 and this I am calling as equation 2. I think you can simplify now and you can get the required results, guys. So I'm dividing these two equations, guys. So L minus 0.1 divided by L minus 0.2 is, so this is 22 divided by 2, right? I just divided equation 2 by equation 1. K gets cancelled, G gets cancelled, and you will be left with this. So this is 11. This is L minus 0.1 is 11L minus 0.2 into 11, guys. So this is 10L. So this is 0.2 into 11 minus 0.1. To simplify this, you can find the value of L, guys. And the value of L. So 0.2 into 11 minus 0.1 divided by 10. So this is 0.21 meters, guys. That's nothing but 210 mm, okay? So the length is 210 mm, guys. So there's only one option with length 210 mm. You can just pick that answer, guys. Or if you want to find the value of K, you can do that. You just substitute in any one of these equations. So this K is, so 0.21 minus 0.1. So this is 22 into 9.81, guys. Simplify this and get the value of K. So 22 into 9.81, so divided by 0.21 minus 0.1. 1962, guys. 1962 Newton per meter, okay. So it's close to 1960, I can say, yeah. This is the answer, guys. Many students make a mistake here. So when they read this word like 20 kg mass is placed, they directly consider this as 20 kg. No, this 20 kg is placed on a pan, which is 2 kg, guys. The pan itself is 2 kg weight. We need to consider that weight also, okay. So try to answer this question, guys. Again, this is a very simple question. A torsion bar with spring stiffness K is cut into n equal lengths. The spring constant for each portion would be. So guys, listen here. So try to answer this question, guys. If I give you a spring of stiffness K, and if I break this spring into 2 equal halves, if I cut the spring into 2 equal parts, what will happen to the stiffness? The stiffness basically will double, guys. So many of you thinking the stiffness will remain same or will decrease. No, it doubles. So basically the stiffness of the spring depends on its length. If the spring length is less, it's more stiff, guys, okay? If the number of coils are less, it's more stiff, okay? So will this hold good? Yes, it will hold good. So the spring stiffness basically doubles. When you again club them in series, you will get the original stiffness, guys, okay? So when you break this spring into 3 equal parts, what will happen? The stiffness of each part will be 3K, guys. So when you break the same spring into 4 equal parts, the stiffness of each part will be 4K. You club them in series, guys. 1 by 4K plus 1 by 4K plus 1 by 4K is 1 by K equivalent. So you will get again K equivalent as K. So if you break this spring into n equal parts, what will happen, guys? So the stiffness of each part will be Nk. So this analogy will hold good for the springs in, the torsion bar, whatever it is, guys. So whether you apply for a linear stiffness for a spring or a rod or for a torsional stiffness, guys. So you apply this for a torsional spring or a rod which is subjected to torsion and torsional vibrations. So this analogy will hold good, guys, okay? The same analogy will hold good. So you can use the same analogy for finding the equivalent stiffness. When 2 springs are clubbed in series and parallel, we have formulas for finding the equivalent stiffness, right? When 2 rods are clubbed in series and parallel, you can also find the equivalent torsional stiffness using the same formulas. And all the analogies that work for spring, so they very well hold good for these torsional rods or torsional bars or the linear stiffness for rods. It holds good in all the cases, guys, okay? So here also it is Nk. So when you break that into n portions, so the stiffness will be n times K, guys. If you want to verify that, you can verify using the strength of materials equations, okay? No, so this holds good, guys. Yeah, so try to answer this question. So logarithmic decrement of a damped single degree of freedom system is delta, guys. So logarithmic decrement is delta. So if the stiffness of the spring is doubled, is saying that the new stiffness is 2 times the old stiffness, and mass is halved. So the new mass is a half. So then the logarithmic decrement of the new system will become, what will be the logarithmic decrement of the new system is? So this is zeta into omega n into TD, guys. So this is a formula for logarithmic decrement. So if you look at this logarithmic decrement, if I further expand this, I'm writing like this: zeta into omega n into this TD, I'm writing it as, so it's 2 pi by omega d, guys. So what is this omega d? If you want to further expand this, you can write it as a function of omega d is omega n into under root 1 minus zeta square. You can eliminate this. You can say now this logarithmic decrement delta is depending on zeta, guys, okay? And if you look at this zeta, how zeta is varying with mass and stiffness, zeta is c by 2 root km, right? Zeta is c by 2 root. So the stiffness is doubled, guys, and the mass is halved. So will there be any change in zeta, guys? There is no change in zeta. When there is no change in zeta, there won't be any change in delta, guys. The logarithmic decrement is going to remain same. So the logarithmic decrement is a function of zeta, and zeta is not getting affected. So when you double the stiffness and halve the mass, okay. So try to answer this question. This is a very basic question, guys. So from the same formula that we have seen just now, the equation of motion for the damped vibrations is given. So the damping factor will be, what will be the damping factor, guys? So compare this equation with mx double dot cx dot plus kx is 0, guys. So the damping factor, damping ratio is nothing but zeta, guys. Zeta is c by 2 root km. So what is c, guys? C is 9 by 2 root k. What is k? So kx, it's 27. What is m? M is 6, guys. If you simplify this, you get the answer, guys. So c by 2 root km. So 0.3535 is. Option C is the answer. So damping ratio, damping factor, all are same, guys. So try to answer this question. 4 linear elastic springs are connected to mass m as shown in the figure, guys. The natural frequency of the system is. So again, very same question that we have been solving, guys. These 3 springs are in parallel. The stiffness is 3K, and this 3K and this K is in series. So for series combination, the equivalent stiffness is K1, K2 divided by K1 plus K2. So K1 is 3K, so into K2 divided by K1 plus K2, guys. What is this? So this is 3K squared divided by 4K. So this is 3 by 4K. This is the equivalent stiffness. So once you get the equivalent stiffness, the natural frequency is under root K equivalent, so by M. So 3K by 4M, guys. So if you want to find in heads, you just multiply with 1 by 2 pi under root, so 3K by 4M. So 1 by 2 pi into root 3K by 4M. 3K by 4M. Option D is the answer, guys. Yeah. So try to answer this question, guys. In the viscous damped vibrations, the logarithmic decrement value over 5 cycles is found to be 8.11, guys. So generally, you remember a formula, guys. If you remember this logarithmic decrement, so it's like xn, so divided by xn plus 1. It's the ratio of 2 successive amplitudes, guys. The ratio of 2 successive amplitudes is e power zeta omega n into TD. In damped vibrations, ratio of 2 successive amplitudes will remain constant, and that is e power zeta omega n into TD. So it is successive cycles, right? So that's why it is 1 times TD basically. So if there are n cycles, guys, so this is xn, so divided by xn plus 5, right? It's 5 successive cycles. It's the first cycle, and after 5th cycle, what is the amplitude? So if you find this, e power zeta into omega n into, instead of 1d, you will be having 5d, guys. This is the ratio of amplitudes. Logarithmic decrement, you just apply log on both sides, you get logarithmic decrement, guys. It is omega into 5 into TD. So basically this is given in the question, guys. So that logarithmic decrement for 5 successive cycles is given as this one. This is 5 zeta omega and TD, guys. This is given in the question. What is the viscous damping factor? Damping factor is nothing but zeta, guys. He's asking us to find the value of zeta, okay? So this is 5 zeta omega n. So this is TD is 2 pi by omega d. Omega d is omega n under root 1 minus zeta square. You can eliminate this. So this is 5 into 2 pi into zeta divided by under root 1 minus zeta square. So this is 8.11, guys. 8.11, okay. So I write like this. So under root 1 minus zeta square divided by zeta, right? Under root 1 minus, this is nothing but, so this is 10 pi divided by 8.11, guys. So now you can square and add on both sides. What do you want to do? You can further simplify this, guys. Basically, 1 minus zeta square divided by zeta square is some constant. What is that constant? This is 10 pi divided by 8.11. So this is 3.87, guys. So this is 1 minus zeta square. This is 3.87 into zeta square. You simplify this and get the value of zeta, guys. So 1 divided by 2.87. And the root of that is 0.59, guys. So I made a mistake somewhere. Sorry, I forgot to square that. So square of this, guys. So you get something close to 0.267, guys. So the damping factor is basically 26.7%, okay. It's close to 25, guys. Only one option is there. Okay. Yeah, so you should be very careful with the calculations, guys. So try to answer this question. A vehicle suspension system consists of a leaf spring and damper. The stiffness of leaf spring is given, guys. Stiffness is directly given in the question. So the problem is slightly simple. So 3.6 kilonewton per meter. And the damping constant of the damper C is given 400 Newton second per meter. So if the mass is 50 kg, so mass is given as 50 kg. So then the damping factor and the dampened natural frequency are. What is the damping factor, guys? Damping factor is zeta. So zeta is C by 2 root km. So zeta is C by 2 root km, guys. C by 2 root km. So the value of C is given in the question. That's 400 2 root km. So this is 3.6 into 10 power 3. Under root, never substitute a kilo inside a root, okay? So very important thing whenever you solve problems, guys. This M. So this is 0.471, guys. So it's a dimensionless number, okay, zeta. So it's a ratio of, it's a dimensionless number, guys. It's a ratio of C by CC, basically, okay? And the next question is the damped natural frequency, guys. He's asking in heads. So first find omega D. Omega D is omega n into under root 1 minus zeta square, guys. What is omega n? Omega n is root k by m. You know what is k? You know what is m? Substitute and get the answer, guys. Root k by m. So this is 6 root 2. So this is 6 root 2 into under root 1 minus 0.471 square. So this is 7.48 radian per second, guys. So if you see this option is there, guys, this is not correct, guys. Many students try to go for this. The units are very important. It's radian per second. Now you convert this into heads. How do you convert this into heads? So the frequency in heads is omega d, so divided by 2 pi, guys. So divide this by 2 pi. So 1.19 heads, guys. 1.191 heads. So option A is the answer, guys. Should be very careful with these kind of questions, okay? So a similar question is there in GATE also. It was asked long back, okay? So I already told you this: whirling speed, whipping speed, the dangerous speed, or the critical speed, all are one and the same. They are nothing but the speed at which the shaft vibrates violently. So that is nothing but the natural frequency, guys. Whirling speed of the shaft coincides with the natural frequency of its transverse vibrations, guys, basically. So the transverse vibrations natural frequency, basically. So basically look at the transverse vibrations. So we have already, you might have seen this. So whenever these rotors are not properly balanced, guys, so whenever there is a rotor on a shaft and that is not properly balanced, what will happen? So when the shaft is rotating, there will be some unbalanced centrifugal force. And because of this unbalanced centrifugal force, the shaft will be violently vibrating, guys, okay? The shaft will be violently vibrating like this. It will be vibrating perpendicular to its length. So this is the length, it will be vibrating perpendicular to length, guys. So those vibrations, we call them as transverse vibrations. The whirling speed that we are referring, or the critical speed or the dangerous speed that we are referring, so we are referring to the transverse vibrations of the shaft, guys. So find the natural frequency of the shaft in transverse vibrations, and if that coincides with the speed of the shaft, then this will be happening, guys. Okay, so it's a concept of transverse vibrations. Okay, so the vibrations are perpendicular to the shaft. That's why we say it's a transverse vibration, guys. Okay, so if the vibrations are along the length, so we call them as longitudinal vibrations. But here the vibrations are not along the length. Torsional vibrations, the shaft will not be subjected to any torsion, guys. So the shaft is inside bearings, right? It is free to rotate. The shaft is free to rotate. Why there will be torsion inside the shaft? No torsion. So there won't be any torsional vibrations. So coupled with bending, and no, there are some bending stresses happening here, but it's not coupled with torsion, guys. Okay, coupled with. So the transverse vibrations, there are bending stresses. Okay, it's not torsional. Yeah. So for the previous case, it is transverse vibration, guys. So try to answer this question. Oscillations of a particle is prescribed by this equation, where t is the time in seconds. So the time taken by the particle to move from the position of equilibrium to the maximum displacement, guys. So from the position of equilibrium to the maximum displacement, how much time it is going to take? Okay, how much time it is going to take? So we need to find the time related to two positions, guys. So if you look at this displacement graph, so displacement graph is a cosine graph, guys. So if you plot this displacement curve, it's going to look something like this. Displacement graph, it looks something like this, guys. So at time is equals to 0, when your time is equals to 0, x is not 0, guys, x is 3. You have maximum displacement, which is nothing but the amplitude of vibration, guys. This is the amplitude of vibration, which is the maximum displacement. And the mass will be vibrating like this. So there is no friction, right? So when there is no friction, so it will come back to the same height. So the vibrations will be happening, guys. Vibrations will be happening, so like this. So I'm just plotting. So what is one cycle of operation, guys? So it started from here. It started from here, and it's moving down to the equilibrium position, and it's again deviating from the equilibrium position, and it again came up, guys. And it's about to repeat the same thing, right? So this is one cycle, guys. This is called as one cycle. And after this, again the same thing is repeated. After this, again the same thing is repeated. So this is called as one cycle of operation, guys. One cycle of operation, and the time it's going to take is TD, guys. The time it's going to take is T. It's a time period, guys. It's not damped, it's undamped. Let me call this as T. So this is the time period, guys. So the time taken to repeat the motion is called as the time period. This is one time period. So the question is, from the equilibrium position to maximum displacement, how much time it takes? It means from the equilibrium position to the maximum displacement, how much it takes. So from the equilibrium position to the maximum displacement, how much time it's going to take, guys? So generally, so this time, it is equal intervals, guys. This is T, and if this is T, this will be T, and so from here to here, so this is T, guys. So these are the 4 T's, okay? So from here to here, if it takes T amount of time, so from here to the maximum position, it takes the same amount of time. From here to the equilibrium position, it takes the same amount. So basically, So this is 4 times t is nothing but the time period, and this t is nothing but t by 4, guys. So if you know what is the time period, you can find out how much time so the mass is going to take. So to go from the mean position to the extreme position, or the extreme position to the mean position, guys. So these times are exactly same because these are natural vibrations, guys. So if these are not natural vibrations, then the time may not remain same, guys. The time may change. So try to find what is the time period of vibrations. So the natural vibrations, x is so a cos omega n into t, or a sin omega n into t, guys. So the coefficient of time is nothing but, so the natural frequency, omega n is directly given in the question, that is 0.25 times pi. A sin, the multiple of time is nothing but omega n, guys. So once you get this, so you can find the time period. So t is 2 pi by omega n. This t is 2 pi by, what is omega n? It's 0.25 by. So find the time period, guys. So the time period is 8 seconds, guys. The time period is 8 seconds. And for each interval, so it is taking 2 seconds, guys. So he's asking us to find, so the time, so the mass takes to go from, so the equilibrium position to the extreme position. So this is small t, which is nothing but the 2 seconds, guys, which is nothing but the 2 seconds. Guys, or in other ways, you can just look at this analogy. So the simple pendulum, I displace the simple pendulum. So initially at time is equal to 0, there is some amplitude, right? So that's why I'm displacing the simple pendulum. I leave the simple pendulum, guys. So when I leave the simple pendulum, what will happen? So the pendulum will come to the equilibrium position, and then it will go again to the other extreme position. Again, it comes back to the equilibrium position. Again, it comes back to the same level, guys. The total time taken is nothing but one time period. So once again it comes here, it again does the same thing. It goes there, it comes back. Again, it goes there, it comes back. So again, it's repeating the motion. So for these 4 distances, for covering these 4 elements, the total time it takes is, so one time period. So, and this I am just representing with a small t, small t. So what is that small t? It's nothing but t by 4. T by 4, guys. 2 seconds. It takes close to 2 seconds. Okay. So option A is the answer for this one. Yeah. So try to answer this question, guys. A machine mounted on a single coil spring has a period of free vibrations. Period of free vibrations is nothing but the natural vibrations, guys. The time period of natural vibrations is t. So if the spring is cut into 4 equal parts and placed in parallel, and the machine is mounted on them, so then the period of free vibrations of the new system is. He's saying that there is a machine, and this machine is on a spring of some stiffness k, guys. So now the time period is t. So what will happen? So if the same machine is mounted on springs, so 4 springs. So and where did he get these 4 springs? So he made this one spring into 4 pieces, guys. I already discussed this. So if you break a spring into some number of equal parts, if I break the spring into, if k is stiffness of the spring, and if I break this into 2 equal parts, the stiffness is 2k and 2k, guys. If I break this into 4 equal parts, what will happen, guys? Stiffness of each portion will be 4k, 4k, and 4k. It will increase, guys. And when you club all of them in series, you will get the original stiffness, guys. Okay, you will get the original stiffness. It is made into 4 equal parts. So the stiffness of each part will be 4k, 4k, 4k. And what is the equivalent stiffness, guys? All of them are now clubbed in parallel, right? So it is 4k, 4k, 4k plus 4k. How many 4s are there? So this is like 16k, guys. The equivalent stiffness is 16k. So what will be the natural frequency? Omega n is under root k equivalent by m. So this is 16k by m, guys. Plus 16k by m. So this is nothing but, so 4 into root k by m, guys. So the new natural frequency basically, so this is nothing but the 4 times the old natural frequency, guys. What about the time period, guys? Time period is 2 pi by omega, right? What will happen to the new time period, guys? So the new time period, so will be So 2 pi by, so instead of omega, now you have 4 omega. So maybe it's omega and 4 omega, guys. So what happened to the new time period, guys? So the new time period is nothing but, so 1/4 of the old time period, guys. It's 1/4. The time period will reduce, guys. The time period will reduce, okay? When the spring is having more stiffness, the restoring force is more, the frequency is more, it comes back very quickly. So the time period, the time taken to repeat the motion will be less, guys. It will reduce basically. So try to answer this question. Again, it's a very simple question. So in vibrations, so far we solved all the questions and all of them were very, very easy, guys. Okay, very basic questions. I can say engineering services level questions. The gate questions are slightly, they're moderate, not complex, I can say. Okay. So for two springs having same stiffness are in series, guys, the equivalent stiffness is. So what is the equivalent stiffness? K1, K2 divided by K1 plus K2, guys. So whenever two springs are clubbed in series, so the equivalent stiffness 1 by K equivalent is 1 by K1 plus 1 by K2, guys. You rearrange the terms, you'll get this formula. So this is K square divided by 2K. So what will be the equivalent stiffness, guys? The equivalent stiffness is half. B is the answer, guys. So try to answer this question. In simple harmonic motion, the acceleration is proportional to, this is a 12th standard question. So acceleration is proportional to displacement, and it is always directed towards the mean position. If you remember that, that's the same thing, guys. Okay. So in simple harmonic motion, so acceleration is always directed towards the mean position, and it's directly proportional to the displacement. So that is a simple harmonic. That's the definition of simple harmonic motion, guys. So what is simple harmonic motion? It is a periodic motion. It's a periodic motion. And can I say all periodic motion are simple harmonic motions? No. All periodic motions are not simple harmonic motions. Only those periodic motions are simple harmonic motions for which the acceleration is directly proportional to displacement and always directed towards the mean position, guys. Towards the mean position. Okay. So if you take an example of a spring mass system, guys, if I take an example of a spring mass system, this is the spring and this is the mass that I'm having, and K is the stiffness. Now imagine this, guys, if I pull the mass and if I leave the mass, what will happen? The mass is executing a to and fro motion, right? The mass is executing a to and fro motion. Let us take some instant, guys. Some instant when the mass is at a distance x from the mean position and the mass is moving in this direction, guys. It is executing a to and fro motion at some instant of time. So the mass is at a distance x from the mean and it's moving in this direction, guys. So what is the force acting on the mass? It is frictionless contact. So the only force that is acting on the mass is because of the spring. What is the direction of that force, guys? The direction of that force is towards the mean position. This is the mean position, right? Towards the mean position. What is the magnitude of that force? X is the deflection of the spring. The force is kx. What is the direction of the spring force? Towards the mean position. Right? So if I ask you what is the force acting on the mass, the force I write it as minus kx. Why minus? The negative sign indicates that the force is not in the direction of displacement. The body is moving in this direction, but the force is towards the mean position. That's why it's minus kx. So this is ma. So it's minus kx, or I can say the acceleration is directly proportional to minus x, guys. It is always directly proportional to displacement. So as the mass goes away from, so the more deflection, the value of x increases. Yes or no? So the restoring force increases and it's directed towards the mean position. So it's directly proportional, guys. Okay. So more elongation, more spring force, more acceleration. Okay. So acceleration is always directly proportional to displacement. So the same thing happens here, guys. When the mass is somewhere here, what happened? The spring is compressed. What is the direction of spring force? It is again towards the mean position. Okay, towards the mean. Always, in simple terms, if the vibrations are happening because of a restoring force, they are simple harmonic in nature, guys. So whenever there is a restoring force, the restoring force will be always directed towards the equilibrium position, the mean position, and it will be always opposite to that of displacement, guys. The spring is elongated, the spring force will be towards its mean position. It's in the opposite direction. And you elongate more, the force will increase more. Okay. So if the vibrations are happening because of some restoring forces, it is a simple harmonic motion, basically, in simple way. Okay. Or this is what you can remember. So the simple harmonic motion is nothing but a periodic motion. And the periodic motion should be such that acceleration is directly proportional to displacement and in the opposite direction. Okay. Yeah. Or if you want to see mathematically, you can see that x is a sine omega n into t plus. This is the SHM equation, guys. You differentiate this, you get velocity. So this is a omega n cos omega n into t plus phi. You want to find acceleration. This is minus a omega n square sine omega n into t plus phi. So the acceleration is, so what is this a sine omega n into t plus phi? This is nothing but x, right? So this is minus omega n square times x, guys. So acceleration is directly proportional to minus x for SHM. Okay. So it's not directly proportional to linear velocity. It's not directly proportional to this. Omega is not angular velocity, guys. That's omega is angular natural frequency. Don't get confused with that. So rate of change of angular velocity. So it is directly proportional to displacement, guys. So a vibrometer. So what is a vibrometer, guys? So vibrometer is an instrument, basically. It is used for finding the amplitude of vibrations, guys. So by how much amount, how vigorously it is moving. Okay, so what is the maximum displacement it is having? So whenever there are vibrations in machines, to find by how much amount the parts are moving, to find the amplitude of vibrations of machine elements, we generally use this vibrometer. And in civil engineering also, for structural designing, we use this vibrometer to find out the amplitude of vibrations and how the structure is behaving at different amplitudes, guys. Okay, it is basically indicates the vibration amplitude, guys. Okay, vibrometer is for noting the amplitude of vibrations. Okay, so at node of the shaft, so whenever there is a node in the shaft, so what will happen to the vibrations? What is this node, guys? So you see this node basically in torsional vibrations. So this is a disk, and so assume this is a shaft which is connected to the disk, and so there is one more disk on the other side, guys. Okay, so there are two disks. So there are two disks, and at the two ends of the shafts. So this is a shaft. There's a disk over here, and there's a disk at the other end. What I can do is I can twist both of them in the opposite direction. I can leave them. When I twist and leave them, so there will be vibrations, guys. So they will be experiencing a twisting and untwisting. Okay. So some portion of the shaft, which is closer to this. So since I'm twisting the disks in opposite direction, so some portion of the shaft which is close to this disk and some portion of the shaft which is close to this disk will be rotating in the respective directions. Maybe this will be rotating in clockwise, this will be rotating in counterclockwise, guys. If both are rotating in same direction, then there won't be any vibrations happening, guys. It will be just a rotation. Okay, there will be no restoring force, there won't be any vibrations. So basically I twist both of them in opposite direction and I leave them. When I do that, they will be twisting and untwisting. So this portion of the shaft you can see, which is very close to this disc, it is moving in the direction of this disc, and this portion of the shaft which is close to this, it will be moving like this. Imagine this. Twist this and twist this. Twist this and twist this. Okay. So it's like you take a towel, you twist the towel and twist the towel. Twist the towel and twist the towel. So you can see the portions of the towel which is close to your right hand will be moving in the direction of this hand, and the portion of the towel which is close to this hand will be moving in this direction. Okay. So when that happens, guys, when that happens, here you can see something. So the amplitude of vibrations or the angular displacement of the shaft will be changing, guys. Okay, the angular displacement of the shaft will be changing. So maybe the angular twist here is more, and as you move, the angular twist of the shaft, the twist is reducing, guys. The twist will decrease. When I twist, the angular displacement, the amount of rotation, so at this portion of the shaft is less. It is further decreasing. It is further decreasing. It is further decreasing, and it's zero here. So now on the other side, it is this portion of the shaft is rotating in the opposite direction. The angular twist is more here. It is increasing. As you go to the free end, the angular twist will be increasing, and it's maximum at the free ends, guys. And there is one point where there is no angular twist, right? So this point is called as node, guys. This point is called as node. Where is this node formed? So the node is formed such that, so let me say this is I1, this length is L1, guys. So from here to here, this length is L1, and from here to here, so this length is L2, and this is I2, guys. The node is formed such that this I1, L1 is equal to I2, L2, guys. I1, L1 is equals to I2, L2. Where is the node formed? Is it formed closer to the smaller disk or the bigger disk? It depends on the value of I, guys. Okay. So if I say like this, if I2 is more than I1, what will happen? If I2 is more, L2 should be less, right? L2 should be less. So this node will be closer to the bigger disk. Okay. So it's something like that. So what is this node? You can see from this diagram, the angular twist is more and it is decreasing, and there is no angular twist here. There is no displacement here. There is no vibration here, guys. So a node is nothing but, so vibrations are minimum. Basically, there are no vibrations, guys. Vibrations are zero at that point. There's no displacement happening, right? That is the node, guys. So node is a point where there is no displacement, guys. So we look at this node, and at this node, so we generally place the bearings, guys. So generally bearings are placed at the nodes so that the bearing will not experience vibrations. So if there are vibrations inside the bearing, what is bearing, guys? It is a fixed part. If you are moving something in the fixed part, what will happen? So over a period of time, there will be wear and tear. The bearing will fail, guys. We don't want that. So we generally locate a node and we try to mount, we try to place the bearing at that particular point, guys. Yeah. So I'll try to answer this question. Two springs of equal length, so but different stiffness. So they are equal length, but the stiffness is different, guys. Support a mass 2 tons in series. The frequency of vibration. There are two springs, guys. The two springs are connected in series. You know how to find the equivalent stiffness, right? So K1, K2 divided by K1 plus K2, guys. K1 plus K2. You simplify this and get the answer, guys. So it's 10 into 15 divided by 10 plus 15. So this is 6 Newton per mm, guys. 6 Newton per mm is nothing but 6 into 10 power 3 Newton per meter, guys. You got the equivalent stiffness. You can find out what is the frequency in hertz. Frequency in hertz is omega n by 2 pi. What is omega n? It is root k equivalent by m. So k equivalent is 6 into 10 power 3, and the value of mass is 2 into 10 power 3. It's 2 tons, guys. So root 3, I can say. Yeah, it's root 3 by 2 pi, guys. Option A is answer. This kind of questions, we solved a lot of questions. I can say 50% of questions from vibrations are like that. Speed of a particle executing simple harmonic motion with amplitude A is half of the maximum speed. At that instant, the displacement of the particle is. Okay, let me read the question again. So speed of the particle. So we need to find speed of the particle executing simple harmonic motion. So with an amplitude A, amplitude is given as A. So with amplitude A. So is half of the maximum speed. The speed of the particle executing simple harmonic motion with amplitude A is half of the maximum speed. He gave the speed, guys. He's saying that the speed of the particle, which is in simple harmonic motion, is half of the maximum speed. The speed is half of the maximum speed. Okay. So at that instant, so when the speed is half of that maximum speed, at that instant, what is the displacement of the particle? Okay. What is the displacement of the particle? We need to find that. So amplitude is given in the question, is the amplitude, guys. So the total energy remains constant, right? So the total energy, I can write it as kinetic energy plus potential energy, guys. So what is the kinetic energy? So you know the speed. Kinetic energy is half mv square. What is v square, guys? So this is v maximum by 2 square plus what is the potential energy? What is the potential energy at that instant? So we don't know what is the potential energy. We need to find that. Half kx square, we need to find that. But we know what is the total energy, guys, because we know the amplitude. half Ka square. So the total energy you can write like this, guys. Half Ka square is total energy, or half, so mv maximum square. Okay, so this is when the speed is maximum, displacement will be 0, and when the displacement is maximum, speed will be 0 in simple harmonic motion. So I can say like this: this Ka square is nothing but m into v max square, guys. Ka square is nothing but m into v max square. So I'll be using this. This is half Ka square. The answer you can see is in terms of A. I want to get in terms of A. So, or let me do this, guys. Let's eliminate the half in all the terms. We have half everywhere, right? So let's try to eliminate the half here, and half here. So you will be having, this is Ka square. So this is mv maximum square divided by 4. This is kx square, guys. So I want the answer in terms of A, Ka square. This is equals to mv max square. What is mv max square? So this is Ka square by 4 plus kx square, guys. You can simplify this and you can find the value of K is there everywhere. Cancel that as well. So what is x square, guys? X square will be a square minus a square by 4. X is under root. So 3a by 4, guys. X is root 3 by 2 times a. So this is the answer, guys. Root 3a by 2. Okay. So this is one important thing. So when the mass is at the mean position, so this is the maximum kinetic energy we have. So there is no potential energy. When the mass is at the extreme position, so this is the potential energy that you can have. That is the maximum potential energy. And there is no kinetic energy. And the total energy is nothing but either you can say the maximum kinetic energy or the maximum potential energy, or at any intermediate position, you will have both of them. So I'll try to answer this question. A block whose mass is 650 grams is fastened to a spring of spring constant 65 Newton per meter, whose end is fixed. Okay, so the block is pulled a distance of 11 centimeters from its equilibrium position. So at x equals to 0 on a smooth surface and released from rest at time is equals to 0, the maximum speed of oscillation is asking us to find out what is the maximum speed, guys. So if you look at the vibrations, how the vibrations are happening, initially we are giving some displacement, and so we are leaving it, right? So let's say something like this. There is a spring mass system. So how am I setting these vibrations? So initially I'm giving a displacement of some 11 centimeters, and then I'm leaving this block, right? Yes or no? So when I leave this block, what will happen? So the block will again go back to the mean position, and it will again displace, and it will come back, and it will come back to the same distance, right? It will again come back to the same distance. So the amplitude of vibrations is nothing but the initial displacement that we are giving. We are not giving any velocity at time is equal to 0. So whatever the displacement that we are giving at time is equal to 0, that will be the amplitude of vibration, guys. The amplitude of vibration for this case is 11 centimeters. If you give 11 centimeters initial displacement and leave it, the mass goes and comes back to the same distance. It goes and it comes back to the same distance. So the amplitude is nothing but the initial displacement that you are giving. So this is 0.11 meters, guys. So if you know the amplitude of vibrations, you can find out what is the maximum speed very easily, right? So the maximum kinetic energy is equals to the maximum potential energy in free vibrations. What is the maximum potential energy? Half K. So if you know the amplitude, square of that. What is the maximum kinetic energy? Half M. So the maximum speed, square of that. So you can find V max square of that is Ka square by M. Ka square by M. You can simplify this and you can get the value of K max, guys. What is the value of K? So K is given in the question 65, the amplitude of vibration, you know, so 0.11, and the mass is given in the question, so 0.65, and you can find what is the maximum velocity. So root 65 into 0.11 square divided by 0.65. You simplify this, you get the answer, guys. The maximum speed is 1.1 meter per second, guys. 1.1 meter per second. So option D is the answer, guys. So these are like very basic 12th standard questions, I can say. So a block of mass m is connected to two springs of stiffness K1 and K2, I showed in the figure. So let F1 and F2 are the frequencies of the block when connected to K1 and K2 independently. So then the frequency of mass m connected to K1 and K2, I showed in the figure will be. So he's saying that, so F1 is the frequency when this mass is connected to this K1, guys. If only mass m is connected to K1, the natural frequency will be under root K1 by m. So F2 is the frequency when this mass m is only connected to K2. So when that is connected only to K2, this is the frequency, guys. So but when K1 and K2 are connected to the mass, the frequency is F. What is this F? So F is nothing but K equivalent by m. What is K equivalent? The two springs are connected in parallel. So this is K equivalent, K1 plus K2 divided by m, guys. So this I write like this. So this is nothing but K1 by m plus this is K2 by m, guys. So this frequency F is nothing but under root. What is K1 by m? K1 by m is nothing but F1 square. What is K2 by m? K2 by m is nothing but F2 square, guys. F is nothing but, so F1 square plus F2 square under root. Okay, so that's the answer, guys. So these problems, we solved a lot of problems, guys. I hope this is clear to everyone. I don't know whether you have made any observation or not. So you get a lot of easy questions in ISRO exam, guys. So don't stick and waste your time solving the complex questions, okay? Are you getting my points? Don't waste time so solving a complex question. So go through the question paper, try to solve all the easy questions and then the medium questions. The complex questions, leave for the end. If you have time, you solve them. If you don't have time, don't need to worry. So many people leave them. So you will also leave them, okay? But don't waste time and lose your score by wasting the time in attempting the tough questions, okay? Yeah. If you don't know the question, you are not getting an idea, just leave it, go for the next question. Okay, it's a game of attempting more questions. Okay, so once you are shortlisted, so you can show your skills of solving the toughest problems in the interview, guys. Okay, so the interview matters a lot for ISRO exam. So the block has a kinetic energy of, so the kinetic energy of the block is given as 3 joules, and the spring connecting the block has an elastic energy, is nothing but the strain energy of the spring is 2 joules. So when the block is at x is equals to 2 centimeters, this is the case, guys. So what is the kinetic energy? So when the block is at x equals to 0. So what is the total energy, guys? So when the block is at the rate x is equals to 2 centimeters, what is the total energy? So that is the kinetic energy plus the elastic potential energy. So that is 3 plus 2, this is 5 joules, guys. This is the total energy. This is the total energy, right? When x equals to 0 at the mean position, what is the total energy, guys? The total energy is the kinetic energy, and that is the maximum kinetic, no potential energy, right? What is that? That is nothing but 5 joules, guys. It's a very simple question. So try to answer this. A simple spring mass vibrating system has a natural frequency n. So if the spring stiffness is halved, so if you reduce the stiffness to half and the mass is doubled, so if you double the mass, what will happen to the natural frequency? So omega n is under root k by m, right? So what is k, guys? So k is k by 2 and this is like 4m. So it will get half, guys. And the natural frequency will become half, right? The natural frequency will become half, guys. So try to answer this question, guys. Under logarithmic decrement, the amplitude of successive vibrations, what will happen to the amplitude of successive vibration? Is it constant? No. So in damped vibrations, I already discussed this. The amplitude of vibration decreases with time, guys. The amplitude of vibration decreases with time, okay? And one important thing here is, so this is the amplitude x0 in the beginning. After one cycle, this is the amplitude. Let me take a different color. So this is the amplitude after first cycle. I call this as x1. So this is x2 and so on, guys. So one interesting here is in damped vibrations, if you find the ratio of x0 by x1 or x1 by x2 or x2 by x3 or you find xn by xn plus 1, it remains constant, guys. That is e power zeta into omega n into t. The ratio of two successive amplitudes will remain constant. If the ratio of two successive numbers is constant, what is it called, guys? It is nothing but a geometric progression. Okay, the amplitudes will be in geometric progression, guys. So it is not logarithmic progression. The decrement is logarithmic decrement. The amplitude decreases logarithmically, but the amplitudes, they are in GP, guys. They're in geometric progression. It's not arithmetic progression. It's not constant. It decreases. Amplitude is constant only in two cases. It's a natural vibration, amplitude remains constant. If it is a steady state forced vibration, amplitude remains constant. But for damped vibrations, the amplitude decreases, guys. So the periodic time of a simple pendulum is, so he's asking us to find what is the time period of the simple pendulum, guys. So take a simple pendulum. So find the natural frequency of the simple pendulum. M is mass of this pendulum. L is the length of the pendulum. So you give a small angular displacement to the simple pendulum. So the pendulum is rotating about point O. So when you give a small angular displacement to the pendulum, so the pendulum goes to a new position, something like this. This is the mass. This is L. A small angular displacement is given to the pendulum, guys. A small angular displacement is given to the pendulum. So now you find what are the external forces acting on the pendulum. So here you will be having a force, which is the gravitational force, mg force. If this is S and this is theta, so this is nothing but L sine theta for small angles. So sine theta can be written as theta. So these are the external forces. So when I displace the pendulum and leave it, it is oscillating, right? It is oscillating, guys. You find what are the external couples acting on this pendulum about this point O. So about this point O, the couple produced because of mass is, so this is mg force. The perpendicular distance between line of action of mg and point O is L theta. This is the couple produced because of mg force. This is the unbalanced couple. Are there any other unbalanced couple acting here? There are no other couples, guys. So we have rotated this pendulum in this direction. So I am adding the inertia couple in the opposite direction. Inertia couple is I theta double dot. I is moment of inertia of the mass about point O. So moment of inertia, so I theta double dot. So plus this is inertia couple plus external couples mg L theta. This is 0, guys. So this is ml square theta double dot. This is mg L theta. This is 0. You can eliminate this mass over here, this length over here. This is theta double dot. This is g by L times theta is 0. What is omega n? So for a simple pendulum, natural frequency is under root g by L, guys. So you need to remember this, guys. Okay, try to remember this because simple pendulum is something which we see very frequently and which we have been dealing from a very long time, from your 12th or 8th standard. I exactly don't remember. So you should remember this, guys. Omega n is under root g by L. This is natural frequency. And what about the time period, guys? Time period is 2 pi by omega n, right? So time period is, it is 2 pi by omega n. This is L by g, guys. 2 pi into root L by g. Option A is the answer, guys. Option A is that. This is the time period of simple pendulum. If I ask you a question, what will be the time period of the simple pendulum? If I take it to the moon, will it change? Yes, it will change because the time period depends on g. Will the frequency change? Yes, it will change. It depends on g. Okay, spring mass, it doesn't depend on g, so it doesn't change. So try to answer this question, guys. Oscillation of a particle is prescribed by this equation. So where t is the time in seconds, so then time taken by the particle to move from the position of equilibrium to the maximum displacement. We have solved this question. I think the answer was 2 seconds, guys. So from the equilibrium position to the maximum displacement, how much time it takes? So from the equilibrium position, so to the maximum displacement, how much time it takes? So this is one cycle. So if you can find what is the time period, so this is the time period, and this is t, this is t, this is t, and this is t. So from the equilibrium position to maximum displacement, what is that? Small t. So 4 small t's is nothing but one time period, guys. So this is t by 4. So find what is the time period, guys. So what is the time period? So this is omega n, guys. So the coefficient of time is omega n, okay? So this is omega n. This is omega n. So t is nothing but, so 2 pi by omega n, guys. 2 pi by omega n. So this is 2 pi by, so 0.25 pi times 4. You simplify this, you get the answer, that is 2 seconds. We solve this problem. So try to answer this question. It's a very simple question again. Yeah, so try to solve this problem, guys. Try to solve this problem. A mass M attached to a light spring oscillates with a period of 2 seconds. So he's saying that, so a light spring mass system. So for a light spring and mass system, so the time period is 2 seconds, guys. So you know what is the time period? So time period is nothing but 2 pi by omega. So 2 pi by omega is 2 seconds. This is 2 seconds, guys. So 2 pi by omega is 2 seconds. What is omega for a spring mass system? For a spring mass system, omega is root k by m, guys. Or this is m by k. So m by k is 2 seconds. M by k is 2 seconds. If the mass is increased by 2 kgs, so the new mass is m plus 2. So the time period increases by 1 second. Now the time period, new time period will be 3 seconds, guys. So the new time period, so will be 3 seconds. So the time period is 3 seconds, and it is 2 pi into root m by k. Now it's m dash, guys. So this is 3 seconds. This is 2 pi under root. This is m plus 2 divided by k. And so divide these two equations, guys. So I'm dividing these two equations. This is 3 by 2. So this is m plus 2. Root k and root k will get cancelled. You will be left with this m. So if I square on both sides, this is 9 by 4. This is m plus 2 divided by m. So this is 9m. This is 4m. This is 8, guys. So 5m is 8. And this m is 8 by 5. So what is 8 by 5? So it's 1.6. Yeah. 1.6 kgs, guys. 1.6 kg is the answer. Yeah. So try to answer this problem. This is a previous engineering services question. And again, it's a very simple question, guys. Many students will have a confusion on this, but yeah. So here you can see, guys. So let's go through the question first. A cantilever beam of negligible weight. So the beam is of negligible weight, is carrying a mass m at its free end. Okay. So and is also resting on an elastic support of stiffness K1 as shown in the figure below. If K2 represents the bending stiffness of the beam, you know what is the bending stiffness of the beam? That's directly given in the question. That's K2, guys. So the natural frequency of the system is, what will be the natural frequency of the system? Now, if you see, guys, if you look at this mass M, this mass M is supported by the beam and the mass M is supported by the spring. So I can say this load is shared by the beam and by the spring. The load is shared. And what about the deflection, guys? If this mass comes down by 1 meter, what is the deflection of the beam? 1 meter. Or what is the deflection of the spring? 1 meter, guys. So here the load is shared by both the elements and the deflection is same in both the elements. So this is nothing but a parallel combination of the two elements, guys. So this beam I can represent with an equivalent spring like this. So instead of beam, I just represent with a spring. So the stiffness of the spring is just the stiffness of the beam. And so we have a mass M over here. And so this is stiff, another spring, K2, guys. I just replace, what is the beam doing? The beam is having some stiffness. So I just represent that stiffness with a spring of the same stiffness, K2. And this is K1, guys, I'm sorry. This is K1 and that's K2. How are the two springs connected? They are in parallel combination. The equivalent stiffness is K1 plus K2. So what is omega n, guys? Under root K equivalent by m, K1 plus K2 divided by m, guys. This many radian per seconds. So K1 plus K2 divided by m, option C is the answer, guys. Okay. So this is a given system. I'm just developing a schematic model of that, guys. Okay. So try to answer this question, guys. Which of the following relationship between the force F on a particle and the particle position X implies simple harmonic motion? What will be the force on the body if the body is in simple harmonic motion, guys? I already discussed this. So this is a spring mass system. So you displace the mass and leave it, guys. You displace the mass and leave it. What will happen? The mass will be executing a to and fro motion. At any instant X, if you see what are the forces acting on this mass, what's the force acting on this mass, guys? There will be a spring force in this direction. If I ask you what is the force acting on the block, the force acting on the block, we write it as minus kx. Why negative sign? Because the force is in the opposite direction of displacement, guys. So what is a force? We generally refer the force in the direction of motion, but it's not in the direction of motion. It's in the opposite direction. That's why we put that negative sign. For systems which are in simple harmonic motion, the force is always minus kx. The force is always towards the mean position, directed towards the mean position. If the mass is here, the force is in this direction, towards the mean position. So only one option is like that. So option A is the answer, guys. Option A is the answer, okay. Yeah, so try to answer this question, guys. This is again a very simple question. A very simple question. So we saw a lot of questions like this. He's asking us to find out natural frequency in cycles per second. Cycles per second is nothing but hertz. So what is the frequency in hertz? So it is omega n divided by 2 pi. That is the frequency in hertz, guys. So it's 1 by 2 pi into under root k equivalent by m. So what is k equivalent? How are the two springs connected? The two springs are connected in parallel combination. 20 plus 20 is 40. The stiffness is in kilonewton per meter. I multiply with 10 power 3. So divided by mass is 100. 100 and 10 power 3 get cancelled. So here you will be left with so 20 in the numerator divided by 2 pi. I think this we already solved. This is 10 by pi. So the answer is 10 by pi hertz, guys, not radian per second. So 10 by pi hertz. This problem I think we solved. I remember solving this. This is 10 by pi. Option A is the answer, guys. Yeah, so some questions are also repeating in ISRO exam, guys. That's one good thing. But very few, I think hardly 20% are repeated. But most of the questions are same, I can say. At least even if you practice previous ISRO questions, that's a very good bet, I think. Yeah. So whirling speed of shaft coincides with natural frequency of, this also we solved, the transverse vibrations. The transverse vibration natural frequency, guys. The shaft is vibrating in transverse direction because of the unbalanced rotor, right? Because of the unbalanced rotor. So this is the unbalanced rotor inside these bearings. So what will happen? So when this rotates, there will be some unbalanced centrifugal forces. The shaft will vibrate violently perpendicular to its axis, the transverse vibrations. So if that frequency coincides with speed of the shaft, that is nothing but the critical speed, whirling speed, whipping speed, or dangerous speed. So with symbols having the usual meaning, so the single degree freedom system is given in the question, represent. What does this represent? So guys, if you look at this question, so if it is mx double dot plus kx, this is 0. Is this? This is nothing but the natural vibrations, guys. Natural vibrations. No damping, no excitation force. So if the equation is like this, mx double dot plus cx dot plus kx is 0. What is c? The damping coefficient, guys. What is this equation? This is for damped vibrations. Do we have any excitation force? No excitation force. Undamped vibration, sorry. So damped free vibrations. This is undamped vibrations. If I have an equation like this, mx double dot plus cx dot plus kx, this is unbalanced force is also there. F naught sine omega into t. Do we have damping? Yes. Do we have unbalanced force? Yes. This is damped forced vibrations. So damped forced vibrations. Forced vibrations with damping. So this is forced vibrations, sorry. free vibrations, guys. This one, let me try to match this. So free vibrations with damping. So this is the equation, free vibrations with damping. So free vibrations without damping. Forced vibrations without damping. Forced vibrations without damping. So mx double dot plus kx. So this is F naught sine omega into t. So there is force, but there is no damping. Okay, that's how it is, guys. So try to answer this question. So in the two rotor system shown in the figure, I1 is less than I2, okay? So I1 and I2 are moment of inertia, guys. A node of vibration is situated. Where is the node of vibration situated, guys? I already told you that the node will be in between these two. Where exactly the node will be? So the node will be such that the product of I1 and L1 so will be equals to I2 L2, guys. I1 L1 so will be equal to so I2 L2. It is something like this. So the node will be so the amplitude of vibrations. This is the amplitude of vibrations. So the displacement, the twist inside the shaft is increasing, and it is more at the free end, guys. It's more at the free end. It is 0 here. So this distance is L1 and this distance is L2, guys. This distance is L1 and L2. So what is more? I2 is more, guys. If I2 is more, so what will happen to this L2, guys? If I2 is more, so obviously L2 has to be less. So if I2 is more, so L2 should be less. So if L2 is less, the node will be closer to the disk, which has more moment of inertia, guys. So it lies between I1 and I2 and near to I2, guys. Nearer to I2. So try to answer this question, guys. Polar moment of inertia, IP, of a circular disk is to be determined by suspending it by a wire and knotting the frequency of oscillation is. So wire and knotting. So basically the disk. So these are two edges, guys, and basically this is the disk. So we can find the natural frequency using a wire knotting mechanism like this. So now you displace this disk and you leave it. So the disk will be vibrating. So it will be undergoing twisting and untwisting, guys. Okay. So it will be undergoing some twisting and untwisting. Okay. It will be undergoing some torsional vibrations. Okay. So in this particular case, so if you try to find the natural frequency omega n here, so omega n is under root, so it's k by omega n is under root k by m, right? So for a spring mass system, it's k by m. But here, so for torsional vibrations, so we write it as k theta by I. So in the place of k, so we write k theta, torsional stiffness. In the place of m, k by m, so we write it as the moment of inertia of this particular disk. So we are taking moment of inertia of the disk perpendicular to its plane. So we also call this as the polar moment of inertia, guys. So if you look at this natural frequency, omega n, I write like this. This is k theta divided by this I. So, or I can say this, let it be like this. So omega n, you can see it is inversely proportional to, so under root of IP. So here it is given as linear frequency. Linear frequency is directly proportional to, what is linear frequency? It's just divided by 2 pi, right? So I can directly write like this. Fn is also inversely proportional to under root, so IP, guys. If I square on this both sides, Fn square is directly proportional to this IP, or I can say the inertia of the disk is inversely proportional to the frequency, guys. Inversely proportional to the square of the frequency. If the frequency is more, it indicates that the inertia is less, guys, for the disk. Option A is the answer, guys. We can estimate the inertias like this. We cannot get the correct value, but we can estimate. Okay. So the acceleration of a simple harmonic motion of a pendulum is proportional to. So this is again multiple times repeating, guys. It is directly proportional to displacement. Acceleration is directly proportional to minus x. Acceleration is directly proportional to displacement, and it is always directed towards the mean position, guys. Speed of particle executing simple harmonic motion with an amplitude A is half the maximum speed, guys. He's saying that the speed is half the maximum speed. Half the maximum speed. Okay. So at that instant, guys, at that instant. So displacement of the particle is, so what is the displacement of the particle at that instant? So I think this we have already solved this, guys. So the answer is root 3 by 2 times alpha. So in the previous case, it was 8, now it's alpha, guys. So the amplitude of vibration is given, guys. So the total energy I write like this. Total energy is kinetic energy plus potential energy. The kinetic energy mass is given as, so half m, so V maximum square by, so V square, right? What is V square? So V max by 2. V max by 2 whole square is V max square by 4. The potential energy is half kx square. We need to find the position x. So that is the total energy, guys. So if you know the amplitude, we can write the total energy like this, right? Half k alpha square. Half k alpha square. So you can eliminate half here, half here, half here, right? And so if you look at this, guys, half k alpha square, that is the total energy. You can also write this as half m V maximum square. So you can just eliminate this. So you can say k alpha square is nothing but V max square. So V max square, so this I just replace with, so k alpha square by 4 plus k x square is k alpha square. You can eliminate this k and k everywhere. And so you can simplify this, guys. You'll get that same thing, I think, root 3 alpha by 2. Okay, so I'm not repeating, guys. Okay. Yeah. So this is all about the questions that we have from mechanical vibrations, guys. So mechanical vibrations, like we have seen, there are around 51 questions, more than 50% of previous ISRO questions. And most of them are repeated and most of them are simple, guys. So don't miss to attempt the questions from mechanical vibrations. So if you don't have time for going through complete theory of machine, so I suggest please go through vibrations. You can skip all of the topics if you don't have time, but that's not recommended. Again, you are going for a competitive exam, you should be good with all the topics, guys. Okay, thank you.